Okay.
Okay, good morning or good evening, whatever. So we have the surreals here, which have a purely infinite part, a real part, and an infinitesimal part. Then we have an exponential map, which takes the purely infinite part into the monomials, the real part into the positive reals. Oh, sorry, this is at times. And the infinitesimal part into 1 plus infinitesimal. So in particular, exp of the purely infinite part is given by the monomials. So the monomials are the exponentials of the purely infinite elements. And therefore, every x can be written, we know, in exponential normal form. So it's a sum of can be written in a normal form in which all the gamma i's, the exponents, are purely infinite, and e to the gamma I is a monomial, and these are decreasing. So then, since we have this normal form, let me just say that I am assuming in this, when I write x in this form, that Ri is different from 0 also. Okay, then once we have this normal form, then it's natural to look for a derivation which behaves in the good way, in the sense that we want a derivation which has already been explained by Vincenzo, which respects the infinite sums and the exponential map. So you have to take the derivative of e to the gamma is e to the gamma derivative of gamma. So we want to take the derivative of the exponent. And more generally, we said that we want some properties of this, which we called SD0, SD1, SD2, SD3, SD4. SD0 was that the derivative of omega is 1. 1 is the Hardy field, the H field property, namely if X is infinite, the derivative is positive. In analogy with Hardy fields, then the kernel should be the reals, so in particular the derivative is non-trivial. Then we already said that we want the derivative to respect the exponential map. And finally, we want the derivative to respect infinite sums. Whenever, of course, this means that if we have a summable family, the derivative of the sum is the sum of the derivatives. And this includes the claim that if the family of I is summable, then the family of the derivatives is summable. And we said that we can indeed cook up such a derivative. And what is critical is how the derivative behaves on the so-called log-atomic numbers. Let me now recall that the log-atomic numbers lambda are the image of the map called lambda. These are the are the infinite monomials such that these are the log atomic numbers. Log atomic numbers. So these are the infinite monomials such that all the iterated logarithms are monomials. And indeed, must necessarily be an infinite monomial. Okay, now what is crucial? So in particular, we need to define the restriction of delta to the log atomic numbers, and this has been done by Vincenzo. Done by Vincenzo last time. Okay. Now, let's look more carefully at the situation here. So it's useful to have a picture. Let me first introduce the notion of, recall the notion of path. So we have introduced infinite paths, but it's useful also to speak about finite paths. So we have omega. Recall that omega are the monomials. A monomial times a real number will be called a term. And then what is interesting is also to consider the non-constant terms. I call them constant because eventually the reals will be the kernel of the derivation, non-constant terms. So a finite path, so if X has a normal form of this kind, then a finite path in X or of X is a finite sequence of non-constant terms, finite sequence Pn n less than some number k, say P0, P1, Pk, of non-constant terms, Pi, such that P0 is a term of X for some I, and Pn plus 1, Pi plus 1, no, sorry, and, okay, I forgot to say something. This will be called an exponent of f, exponent of x. So a finite path of a surreal number x is a finite sequence of paths such that the first term, P0, is a term of x, in the sense is one of the Ri E gamma I. And the rest of the sequence, the tail of the sequence, P1, Pk, so this is a sequence of a shorter sequence, is a path of the exponent gamma I that we have chosen. So I hope this is clear. And an infinite path is defined similarly, but it's infinite, no? An infinite path Pn is defined similarly. Okay. Now, given X, it may happen that, okay, let me first introduce, let R bracket lambda is the class of logatomic numbers, be the smallest this is the smallest subfield of no containing the reals and the logatomic enclosed under exp log and sum of summable families. So this contains properly, maybe I should do it in the next page, but the next page is already busy, so let me add one page here. Okay, we have the following picture here. We have the transseries, the logarithmic exponential transseries, which are included in the exponential logarithmic transseries, which are included in what I call the bracket of omega, which is the smallest subfield containing all the logatomic elements of the form log n times or of omega. And then we have this bigger field. And finally, we have the surreals. Okay. I already spoke. This is a new entry here. It's non-trivial to show that it's included properly in the surreals. Let me take some representatives here. So in the transseries, we may have something like sum over n log omega to the minus n. In the EL series, we may have e to the minus sum over n log n times of omega, which can also be written as 1 over the infinite product of log n times omega. In the bracket of omega, and not in the preceding ones, we may have something like sum over n natural number minus exp n times of omega, which is of course also here. Here we may have something which we may have, for instance, lambda minus omega, which will serve as an integral of this guy. So if you take the derivative, you obtain that guy. Recall that we have here the surreals. Here we have the convex hull of the reals. Here we have lambda 0, which is omega. Then we have lambda 1, which is the log of omega. And then we keep going. We have lambda alpha for every ordinal alpha. which, and we know that lambda x minus 1 is the log of lambda x.
Sorry, Alessandro. So yes. Log of omega is lambda of minus 1, right?
Minus 1.
Okay, thank you.
Minus 1, and this is minus omega. Okay, now these subfields can be characterized in terms of paths. This guy here, the bracket of lambda, is exactly the class of surreals such that every infinite path enters or intersects lambda. So if you take an element in the bracket of and if in the bracket of lambda, any path, any infinite path, sooner or later will encounter a log-atomic element. And then from that point on, that path will never bifurcate, because if you are in a log-atomic number, the path starting from a log-atomic number is necessarily given by the logs of the iterated logs of that number. So there are no sums anymore. So if once you enter lambda, the path will never bifurcate anymore. Instead, the bracket of omega can be characterized as the class of surreal numbers, such that, maybe let me make some more space here. Such that every path enters log some log of omega, some iterated log of omega. I put Z because it could also be exp. So let's say that log minus 1 omega means exp of omega. But of course, if it enters exp of omega, it will also enter omega at the next step, and at the next step, it will enter log of omega. So I could put Z, the natural numbers instead of the integers equivalently. While here and here, there are some restrictions that I explained last time. So in here we have a restriction on the nesting of iterations of exp, and here you have a uniform nesting of iterations of both log and exp, but I don't want to comment it anymore. So, but they live here. So this is the situation. Okay, now let's see how the derivation is connected with the notion of paths. Suppose we are in, suppose we have paths and derivatives. Okay. Suppose we have a surreal in, which is just a term, so a real times a monomial. The monomial, of course, here I can take gamma, alpha, beta, and delta purely infinite. So we have e to the gamma, R1 e to the gamma. Gamma will be purely infinite if this is a monomial, so gamma will be again some finite or infinite sum. Let me write it in this form. Gamma will be purely infinite, so maybe the first monomial is this one, R2e to something else, and then plus delta. Delta is again purely infinite because it's part of gamma, which is the exponent. So I can make a picture of X like this. So it resembles a tree. so if I put E and then I put some children in this tree, it means that these children must be summed up together and they form the exponent of E, and so on, right? So once we have the normal form, and in this situation, I continue this path if X is in the bracket of lambda by prolonging this. Here I have highlighted the three paths. One is here, one is here, and one is here. Of course, this path maybe can be prolonged, but suppose that alpha, beta, and if alpha, beta, and delta are logatomic, then the path becomes then their paths are linear in the sense that if that the picture will look like this. No further bifurcations. Because if delta is logatomic, a path starting from delta, the next term will necessarily be the log of delta, the log of delta, and so on. So this is the picture you have to keep in mind. So you have a surreal number. You write the tree induced by the iterated exponents and the corresponding terms. And you look for a set of paths which sooner or later encounter a logatomic number. If X is in the bracket of lambda, this can be done. So if X is in the bracket of lambda, certainly there exist paths of this kind. So you fix such a set of paths. And of course, the rules of the derivations, the fact that derivation commutes with exp and infinite and sums, gives you that the derivative of X is necessarily given by a sum of terms, each corresponding to the path. So the first path here gives you this, the second path gives you that, and the third path gives you this. So you can just stop at the first time you meet a logatomic number, you stop the path there. You can also continue, but doesn't matter. This expression will not change. If you stop at delta or log delta, this expression will not change. Why it will not change? Because here, sorry, there is a mistake here. Here you have put delta, right? Yes. Because the derivative of delta, if delta is slow, the derivative of delta is equal, if delta is logatomic, delta will be e to another logatomic. So this is going to be delta itself log derivative of the log. If delta is logatomic, no? So it means that if you stop here, if you consider this path or this path, the expression for delta x remains the same. So this is so you will see here that the derivative of x is a sum of contributions, each coming from a different path. But of course, this will be true regardless of the fact, regardless of whether alpha, beta, and gamma are in logatomic or not. But if they are logatomic, you already know how to compute the derivatives. So maybe they are, for instance, iterated logs of omega. This is the best case. But because then you are forced to define the derivative in a certain way. But even if they are logatomic, if you know the derivation restricted to the logatomic, and Vincenzo explained you how to do that, if you start with, if all the paths end up in a logatomic, then necessarily the derivative is a sum of contribution, each coming from from one of the paths. So these are exactly what Vincenzo called the path derivative. This is the first term here is the path derivative of this path. And it's one of the contributions to the derivative of x. And of course, you need to know derivative alpha, derivative beta, derivative of delta. So each path contributes as a product in which the last part is the derivative of the logatomic number where you arrived, the leaf of the tree. And then you take the product of the terms that you have encountered along the path. And this is forced by expanding the derivation, using the fact that derivation respects exp and infinite sums. You are forced to do this. So, okay. The problem is that this works well if you are in the bracket of lambda. But as we said, that the bracket of lambda is properly included in the surreal numbers. So there might be situations in which you have paths which never meet a logatomic number. And we have to decide what to do in that case. Okay, now we have that the most difficult theorem of is the following. Sorry, I didn't explain exactly what this tree is. This tree, the nodes of this tree, let me write it here. The nodes of this tree are the finite paths of the root. The root is, in this case, x, which is a monomial. If instead of a monomial, you take a sum of, which is a term. If instead of a term, you have a sum of things, a sum of monomials, then it's not a tree, it's going to be a forest. Doesn't have a unique root. But anyway, the nodes of this tree, or in general a forest, are the finite paths. So you consider, and the infinite paths are exactly the infinite paths in this tree. And each infinite path gives a contribution to the derivative as explained by Vincenzo. But indeed, this infinite path will only contribute for a finite, only a finite portion of the path will actually contribute. Because then you can, whenever you arrive to a logatomic number, you can stop there. And if you keep going, you get the same contribution. So this is the idea of the definition of the. So the main theorem, the difficult theorem is the following. Difficult theorem, which I will not do. This is the sort of things that maybe Vincenzo would like to do, but certainly not me. The difficult theorem is the following. which is that this can happen, but this is what we usually call when we work together, the Christmas tree. This cannot happen. So there are no Christmas trees. This is the most difficult theorem. There are no Christmas trees in the surreal numbers. So in which sense? So you the root here is, this is let's say RE to the gamma, and then gamma maybe is a sum of 3 terms, and each term has its path, and so on. And maybe this is another RE to the beta. So if you start in the tree of all finite paths, starting from a given term, you have some restrictions on the kind of trees that can arise. Some trees can arise and some other trees cannot. And what is so special about the first one and not the second one? Okay, so let me give, well, here in this picture, here you have, let me explain a bit better this picture. Here you have, let me draw it, let's say alpha, beta, delta, these 3 surreal numbers. So this alpha, beta, delta are terms, are non-constant terms. So this means that the root x is RE to the alpha plus beta plus delta. Okay, and we are assuming that this is in normal form. Normal form. So in particular, alpha dominates beta, which dominates delta, right? Because we always write things in decreasing order, the terms appearing in a sum. Okay, let me call a path, an infinite path. Infinite path of x an infinite path of x Pn is small if for every big enough n in some sense it's eventually rightmost. It's eventually a rightmost path. So this guy here is small, but this one is not small because you can take a smaller bifurcation, you know. So if for every big enough n, Pn is equal to Rn e to some exponent, the exponent will be purely infinite, something like sum of some other real numbers, let's call it AI, some monomial mi, plus or minus Pn plus 1. So where Pn plus 1 is small, namely it's smaller than all the other terms appearing at the same level. And here all the MIs are purely infinite monomials, because we are assuming that this is written in normal form, so the exponents are always purely infinite. You expand the exponents, and Pn plus 1 appears as the smallest part of the exponent. So if this is, let's say, if this guy here is if this is Pn, say, Pn plus 1 is necessarily this one, if you want it to be small. So if you go straight, you are not following the smallest path. But if you arrive here and then you keep going right, then you are following the smallest path. The smallest path is the one which is. So the theorem says that every path is eventually, every infinite path is eventually the smallest, a small path. And sorry. I said it wrong. I said it wrong. So the theorem says every infinite path of X either enters, let's call it Pn, either enters the log-atomic numbers, so either encounters a log-atomic number, or it is a small path. So in other words, why this picture, if it enters a log-atomic number, then it stops bifurcating. So the only possibility for an infinite bifurcation, so let's consider this picture again. Why this cannot happen? Because you have this central path here, which obviously doesn't reach any log-atomic number. Why doesn't it reach any log-atomic number? Because if it reaches a log-atomic number, it would stop bifurcating, but instead this keeps bifurcating, right? So this doesn't reach a log-atomic number, the central one, but it's not a small path, because there are paths smaller than it. No, I mean, it's not eventually rightmost. It's not eventually rightmost, but nevertheless doesn't meet a log-atomic number. While here, there are paths which keep bifurcating. So this path here on the left picture, the rightmost path doesn't reach a log-atomic number because each of its term as an exponent which is not log-atomic, and so the term itself cannot be log-atomic because the exponent of a log-atomic is always log-atomic. But so this path doesn't reach a log-atomic number, but nevertheless, but it's small, so it's okay. It's okay. And all the other paths, except this one here, if you follow another route, for instance, if you follow the leftmost path, you necessarily meet a log-atomic number. So this is the situation. So this theorem justifies the fact that when you define the derivative, so if you are in the bracket of lambda, you may define the derivative. This is more or less a comment on what Vincenzo already did. I'm not saying anything new, really, but I'm making just some pictures to illustrate the situation. If you are in the bracket of lambda, you define the derivative of a sum of contributions, and it's fine. Essentially, it's forced if this path that you are considering meet a logarithmic number. If there are some, if you want to take the derivative of this guy here, this, you don't need to worry about this one because this one doesn't exist. So this Christmas tree doesn't exist. So you don't need to worry about this. What do you do to define the derivative of this? Again, you define it as a sum of contributions given by the various paths, but you only consider the paths which meet a log-atomic number. And you define the sum of the contributions given by those paths. So you ignore completely the small path. So the small path, this one, will not contribute to the derivative. And it's lucky because otherwise you wouldn't know what to do with this small path, right? But luckily, this, first of all, it's small. And so in some sense, you are legitimated to ignore it. Secondly, even if you ignore it, in some sense, you are not completely ignoring it because this small path is an accumulation point of paths which instead you are not ignoring. Because if you keep going in this direction, but then you change direction, you are not ignoring this one, 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 you are only ignoring the last one, which is small. And it's so the path that end up in a log-atomic numbers, in some sense, are dense in the class of all paths. And so you only consider the contributions coming from those. Okay, this is just what I wanted to say as an illustration of the definition of the derivative given by Vincenzo. Now let me and recall that the derivative given by Vincenzo is in some sense, so let's come back here. So we have these various subfields of the surreals. Okay. Now we have a derivation. There is a simplest derivation. There is a simplest derivation satisfying SD4, SD0, SD4. And this derivation, the restriction to lambda, is given by the formula that Vincenzo explained. Its restriction to lambda is given by derivative of lambda equal, what was it? Was an infinite product. Let me remind, the formula is log n times of lambda over a product. Just a moment. Indexed by the ordinals of L minus alpha, which roughly speaking should be thought roughly speaking as log alpha times of omega. and alpha ranges over all the ordinals such that such that lambda minus alpha becomes bigger than some log n lambda. How was it? Just a moment. Vincenzo, are you online to help?
Yes, so you have to take all the alphas such that log alpha omega is greater than log n of lambda for some natural number n.
Log alpha, log minus lambda minus alpha is smaller, bigger.
Log alpha omega.
No, log alpha omega is lambda minus alpha, right?
Okay. So you want to say there exists a natural number,
yeah,
such that log n times of lambda
log n times
is less than lambda minus alpha.
Okay. So alpha ranges over this alpha ranges over the ordinals with this property. Doesn't really matter why we end up with this formula. Let's just observe that the derivative of lambda minus omega is what I said before, the product log is this, while the derivative of log n times of omega is the product n minus n log n times of omega. So this is the reason why this analogy is the reason why lambda minus omega, roughly speaking, should be thought as logarithm omega times of omega by virtue of this analogy. So if you take the logarithm n times of omega and you take the derivative, you end up with 1 over this finite product. And if you take the derivative of lambda minus omega, by the way it's defined, you get this 1 over an infinite product of the previous logarithms. Okay, this is just this is what Vincenzo did. Okay, now some properties. Here everything is determined by the restriction of delta to lambda. Here everything is determined by nothing, the fact that the derivative of omega is 1. And on the surreal numbers, we have some choice. So there are several derivatives. And our derivation is the one which makes the simplest choice. And the simplest choice is just to ignore essentially the one that has been explained by Vincenzo. So we ignore the paths which do not arrive to lambda. And on the path which arrive to lambda, we use this formula here. Okay, this is the situation. Now I want to speak about integrals. What about integrals? So if the derivative of x equal y, we say that x is an integral of y. Say x is an integral of y. Of course, this is defined only up to a real, because the kernel of the derivative is given by the reals. So this is defined up to a real constant, the reals. So now we may wonder whether the derivative is surjective. So namely, you have integrals. So the situation is, in the surreal numbers themselves, you have integrals. And also on the transseries, you have integrals. And also on the bracket of lambda have integrals, but in the other places, in the bracket of omega and in the LE series, you don't have integrals. And it's easy to see why you don't have integrals. And the reason is the following, that this guy here, 1 over this product belongs to the bracket of omega, but its integral, lambda minus omega, does not. Lambda minus omega is here. So you have an element in the bracket of omega whose integral is outside. And it's not possible to redefine it. You can easily deduce that it will not be possible to redefine the derivative on the bracket of omega in order for this guy to have an integral. Why? Because on the bracket of omega, the derivative is unique. You cannot change it if you want the derivative of omega to be 1. So if you had another object here serving as an integral, you would deduce that it's easy to exercise, it's easy to deduce that lambda minus omega will differ by a real number, by that guy, but the real numbers are included everywhere, so the lambda minus omega will be itself in the bracket of omega, which does not. So I hope more or less I convince you, maybe not, but the fact that in the surreal numbers, you have a derivation with all the properties. This derivation, its restriction to the bracket of omega is unique, but in the bracket of omega, you have an object whose integral goes outside, necessarily implies that on the bracket of omega, the derivation cannot be surjective, given the fact that on the bracket of omega is necessarily the restriction of the derivation that you have on the surreals. Okay, what is the situation in general about integrals? I have to now speak about H fields. This has been H fields. So you have K, an ordered field with a derivation delta. So K, I think I already gave this definition, is an H field. Do you say an H field or a H field, with N or without? Some English speaker. I'm not sure. An H field on Google Translate is with N. I cannot hear you really. So you're speaking.
Margaret says in the chat that it's an H field.
An H field. Okay, good to know. Okay, it's an H field if two properties, x bigger than every constant implies the derivative of x bigger than 0, and big O is the kernel of delta plus the infinitesimals, where big O is the ring of elements bounded by a constant in absolute value. And mu is the unique maximal ideal. So is the set of elements whose inverse is not finite, is not in big O. And so these two properties, which I already commented, are true in every Hardy field, and they form the axiomatization of H fields. And you have some consequences of these axioms. Define, which this has already been done by Lau, x dagger to be the logarithmic derivative. So if you had a logarithm, it would be the derivative of the logarithm. Then you have the following properties, which has already been illustrated by Lau in the context of Hardy fields. If x, now I should really redefine I'm interested in the case, consider the case in which the kernel is given by the reals. So K contains the reals and the kernel is given by the reals. Otherwise, I need to redefine the domination relation, because domination relation has been defined considering the standard valuation. Otherwise, I should consider the valuation induced by this valuation ring big O. Right? And by the way, if the kernel is given by the reals, point 2 is redundant. It's automatically satisfied. Then we have both the derivative and the logarithmic derivatives respect the domination. In the following sense. So let me write something. There are some exceptions. You have to there are some exceptions. You have to assume that certain elements are not in the class Archimedia, not equivalent to 1. So they are infinitesimal or infinite. Then so this is a kind of L'Hopital's rule. So x dominates y if and only if the derivative of x dominates the derivative of x is dominated by the derivative of y. Same thing if they are comparable. Same thing if they are asymptotic. So, well,
sorry, Alessandro.
Yes.
I'm not sure for the logarithmic derivative that the second one changes the comparison. X dagger.
The second one.
Yes, Alessandro. I think the second one.
Yes.
The left-hand side should be flipped the other way around. All the inequalities should go the other way. So xy should be infinitesimal.
So this one, like here.
No, that was one correct. It's the left-hand side which is it's just a repetition of the previous line written this way.
Sorry. So what should I say? Sorry. So these are the infinite case, then the infinitesimal case, like this. But then I have to flip the other side. I have to flip the other side as well.
Yeah.
No. The other side is correct because it's in the infinitesimal case, being smaller means that the logarithm is bigger.
Okay, good. then you have that if x and y are asymptotic, maybe not equivalent to 1, then the derivatives are asymptotic. This is a kind of L'Hopital rule. And but then there is the strange one, which Lau already commented, that the derivative is always smaller than the logarithmic derivative. I mean, in the good cases. So this is a kind of strange. This last property is important in order to understand when an H field has an integral, or at least an asymptotic integral. So in some sense, between all the logarithmic derivatives and the derivatives, there might be a gap or not. And the existence of this sort of this gap is an important property of the H field. So let me say it more precisely. More precisely, we have the following result of Rosenlicht. By the way, yeah, Rosenlicht. Is this when 83? When was it? I don't know.
I think 87, but I could be wrong. So if someone knows better, let us know.
Okay. Suppose you have an H field. And so let me write X between brackets as the Archimedean class of X. So in some sense, it's the valuation, but I don't want to use the valuation because I don't want to reverse the order. So an Archimedean class is bigger than another Archimedean class if the representative is bigger than the representative. So, because with the valuations, everything is reversed, the order is reversed. Of course, here I'm considering X different from 0. Okay, now there is an important set which is called psi, let's say Rosenlicht psi set, which is the set of all logarithmic derivatives of elements which are not equivalent to 1 and different from 0. So this is, recall that this is X dagger, right? So this is are the classes of these guys here, these Y daggers. So, and it's natural to try to consider the infimum of these Archimedean classes if it exists. It's something which will be bigger than all these other guys, right? So the infimum may or may not exist. Let's see what happens in both cases. So psi may or may not have an inf, in the sense the infimum of the Archimedean classes. But then you have the theorem that if the Archimedean class of some element, if X is in elemental of K, and its Archimedean class is different from the infimum, which includes the case in which the infimum doesn't exist. So this holds vacuously if the infimum doesn't exist. Then X has an asymptotic integral. So there exists Y such that the derivative of Y is asymptotic to X. Say Y is an asymptotic integral of x. So there is at most one exception. So either everybody has an asymptotic integral, or there is at most one exception in terms of Archimedean classes. Everything which is not in that Archimedean class has an asymptotic integral. There is at most one exception. So this is a beautiful result. The proof is a very nice trick. Essentially, you want to compute the integral using derivatives, because in an H field, you only have derivatives. You can only take derivatives. But cooking up derivatives of certain elements and making certain quotients, you cook up an asymptotic integral of another guy. There is an formula that you can write, but it's not important for this talk, and you may look it up.
About the reference, Alessandro, I think it's the 83 paper, as you said, the
83.
rank of a Hardy field, but which is done for Hardy fields.
Okay, it's done for Hardy fields, but the proof is very algebraic, so it can be extended to H fields, right? So, okay, now we want to try to understand whether the surreal numbers have asymptotic integrals. Eventually, we are going to show that they have integrals. The trick is first show that they have asymptotic integrals and then iterate, keeping asymptotic integrals until you get an actual integral. So, but let me first make an example of the theorem of Rosenlich. Example. Consider K equal R of x e to the x ordered for x bigger than the reals, and take the derivative, just the usual derivative with respect to x. Okay, so this is an H field. K is an H field with n H field, an H field. And let's compute the psi. Psi is the class of all the f over f Archimedean classes, such that f is not equal to 1, not comparable to 1 and different from 0. Okay, now f is a rational function in x e to the x. So now given G, say, in K, no, given F in K, we know that F is comparable to a monomial of this field. A monomial of this field is a power of X times a power of e to the X, with m and n possibly negative, right? Then, if you take the logarithmic derivative of f, by the properties of H fields, the logarithmic derivatives respect the Archimedean classes. So if f is equivalent to this guy, the logarithmic derivative will be equivalent to the logarithmic derivative of this guy. So we can simplify the computations. We just need to consider the logarithmic derivative of this monomial here. So we get that this is in the same Archimedean class. So what is the logarithmic derivative? It's the derivative of mx to the m minus 1 e to the nx plus xm e to the nx divided by em e to the nx, right? So this is the, I just took the derivative of this guy and divided by itself. So this is equal to m divided by x plus n. And depending on whether n or m are 0 or non-zero, this is equivalent either to 1 or to 1 over x. So if n is different from 0, it's equivalent to 1. If n is equal to 0, it's equivalent to 1 over x. So this means that the psi set has just two Archimedean classes, the class of 1 and the class of 1 over x. So the infimum, so it has an infimum. The infimum of the psi set is 1 over x because it's smaller, 1 over x than 1. And indeed, everything, if g is not equivalent to 1 over x, g as an asymptotic integral, indeed as an integral, as an asymptotic integral, confirming Rosenlicht theorem, if you didn't believe it. And of course, 1 over x itself doesn't have an asymptotic integral because the integral of 1 over x is log x, but it's not there, right? So it doesn't have even an asymptotic integral. So there is nothing comparable to log x there that, so there is at most one exception for the asymptotic integral. So x squared has an integral, x3 divided by 3, but 1 over x doesn't, and it's the only one in this guy. So keep in mind this. We have this psi set, and we have computed the psi set in a specific example. Now we want to make something more difficult, compute the psi set in the surreals. Actually, it will be the psi class in this case. But let's make first let's first prove another result from asymptotic integrals to integrals. Okay, suppose that K is an H field. And suppose that the field itself is just a Hahn field. So it's a field of the form generalized power series, the whole field, not a subfield. And suppose also that the derivative respects infinite sums. And the reals have zero derivative, say. So under these assumptions, there is a theorem. I mean, this is a special case of a more general result proved by Kuhlmann and Matuszynski, I think. And I mean, it's related to various things. Kuhlmann, Matuszynski. So if in this particular case, they proved a more general result, but as an asymptotic integral, then it has an integral. It has, the derivation is surjective. Okay, the proof is the following. Let me just write special case of. Proof. Okay, let AI be the asymptotic integral. So you get for every element different from 0, you can associate to it the asymptotic integral. So without loss of generality, we may take the asymptotic integral to be a real number times a monomial and non-constant, because the asymptotic integral is defined up to everything is asymptotic to a real number times a monomial. So the asymptotic integral can be defined up to asymptotic equivalence. So you may have, you may decide that the values are just the real numbers times the monomials, and is not going to be a real number because the derivative of the reals, we are assuming that they are 0, and here we are taking k different from 0, right? So we have an asymptotic integral such that x is asymptotic to the derivative of its asymptotic integral for all x. So you can do asymptotic integrals. Now you construct inductively. You want to iterate the asymptotic integrals. T0, T1, T2, and so, non-constant terms.
Alessandro,
Yes.
sorry about the reference. I think it's direct consequence. We use it as a direct consequence of Franz Victor Kuhlmann theorem.
Okay, okay.
Just
which
to be
which
precise.
year? Which year?
Oh, it's, let me.
Okay.
It is 2009, I think. Thank you. Sorry.
Construct inductively a sequence such that T alpha for alpha ordinal is the asymptotic integral of x minus the sum for beta less than alpha of the derivative of T beta. Actually, the derivative can be also taken outside of the sum because we are assuming that it commutes, assuming that x minus this sum is different from 0. Otherwise, if it's 0, you have already reached an integral, right? So so for instance, T0 is just the asymptotic integral of x. And T1, if the derivative of T0 is different from x, then T1 is the asymptotic integral of x minus the derivative of T0, etc. So you cannot continue forever for all the ordinals. So there exists alpha, an ordinal, such that you stop. And at that point, the derivative of the summation beta less than alpha of T beta, which is the same as the sum beta less than alpha of the derivative of T beta, is necessarily equal to x. So there are a few things to verify, in particular that this sequence is decreasing, but this comes very easily from the definition of asymptotic. Recall that x is asymptotic to y if and only if x minus y is dominated by x. So using this fact, using the fact that the asymptotic integral gives you something asymptotic to the derivative, and using this definition of asymptotic, then you prove easily by induction that this sequence of terms, which are defined in this way, is really decreasing. So each time if you arrive at certain point and you reach an integral of x, you stop. Otherwise, you keep going and you define the next term as the asymptotic integral of x minus the sum of the derivatives of the preceding ones. So in some sense, this sum serves as, not that one. This one without the derivatives serves as an approximate integral. You get better and better approximations of the integral. And since you range over the ordinals, and since you are living inside, and all these sums always make sense because you are working inside a full power series field, not a subclass, but not a subset. Since you're working in a full power series field, so all possible sums that you can imagine make sense, and M is a set. M a set group, not a proper class. You must necessarily stop at some point, and when you stop, you have really reached an integral, right? So it's not. So if you have a field of this form and you have asymptotic integrals, then you have integrals. Now let's come to the surreal numbers. Let's look at the situation in the surreal numbers. The surreal numbers, first of all, we need to check that they do have asymptotic integrals. So we have to compute the psi set, Rosenlich's psi set for the surreals. Secondly, the surreal numbers are not exactly a field of this form, but are a directed union of fields of this form. And so we have to take some care. Okay, let's come to the surreals. The first claim is that no, the surreals with the simplest derivation given by Vincenzo, explained by the simplest derivation, the surreals do have asymptotic integral, have asymptotic integrals. Okay, so let's compute it. So it will be useful to have this picture in mind again. Here you have a lambda 0, lambda minus 1, lambda minus 2, lambda minus omega, etc., which are co-initial in the infinite surreals. Okay, the idea is the following. You have lambda 0, lambda minus 1, lambda minus 2, and so on, which are just log omega, log omega, and so on and so. And they all have integrals. At some point, however, once you have all these lambdas, you may form 1 over the infinite product of the lambda minus n for n an integer. And this guy doesn't have an integral in the bracket of omega, but it has an integral, and which is lambda minus omega. So in some sense, this sequence of lambdas are obtained either by taking the logs of the preceding one or the integral of a product based on the preceding ones. So you need all of them to have integrals. If you don't have all of them, you will not have integrals. So this is roughly the idea. So let's compute the psi set, the psi class of the Surreals. So again, this is, you have to take the Archimedean classes of the logarithmic derivatives. Okay, in the Surreal numbers, however, we have an actual logarithm. So the logarithmic derivative is really the derivative of the logarithm. Okay, now, if you have an element which is not, this is the logarithm. You are considering the logarithm of elements x which are not in the Archimedean class of 1, namely which are either infinitesimal or infinite. So you are considering the logarithms of the infinitesimal elements and the infinite elements. And the logarithms are necessarily infinite. So this coincides with the class of the derivative. So the log is surjective on the positive elements. So you might just take the logarithm, the derivative of all possible y's. Maybe I should put, sorry, log of absolute value of x if you want to be very precise. So this coincides with the log of the y's such that y is infinite. Because the log of those x's are exactly the infinite y's, positive or negative. Okay, you may just consider the infinite monomials rather than the infinite y's. So you just take the logarithm of the infinite monomials is the same, because each element is in the same Archimedean class of a monomial, and taking the derivatives respect the Archimedean classes. So the Archimedean class of, if y is in the same Archimedean class of m, the derivative of y is in the same Archimedean class of the derivative of m. So you suffices to consider the monomials. Now, by this picture here, which maybe I should color what? Green, maybe. By the green picture, the infinite monomial, this is co-initial. You can just take the derivatives of this lambda minus alpha for alpha unordinal, because this lambda minus alpha will be co-initial in the derivative of the infinite monomials. Recall that the lambdas are monomials, are infinite monomials. So this class that I wrote here is co-initial in the previous one. And since you're interested in considering the inf of psi, if it exists, you may as well consider this subclass. Okay, now by the formula given by Vincenzo for the derivative of lambda minus alpha is 1. Lambda minus alpha is a kind of iterated log. So this is 1 over the product for beta less than alpha, then the lambda minus beta. Recall that lambda minus alpha is the integral of, is this right? Or it's only in the limit case? No, I'm a bit confused now. This is correct also in all cases.
Yes, it's correct everywhere, yes.
Everywhere, okay. So you get this guy. Okay, now, okay. What is this? This is by definition, the product is defined using, infinite products are defined using infinite sums, exp and log. So by definition of infinite product, this is e to the minus infinite sum, beta less than alpha, of, then you have to take an additional log because you put an exp. So it will be minus beta minus 1. Is that correct? Minus 1 or plus 1? Minus 1, right? Yes. Okay. The ordering, and note that the exponent of this exp, of this e, is purely infinite. Now, the Archimedean classes of the monomials are ordered exactly as the exponents of the, so if a monomial has the form e to a purely infinite, the ordering of the Archimedean classes corresponds to the ordering of the exponents, these purely infinite monomials. So now observe that this class of infinite sums, lambda minus beta minus 1 for alpha ranging over the ordinals, has no inf in the Surreal numbers. Why it has no inf in the Surreal numbers? This is an exercise, but roughly the idea is that the inf should be the sum over all the ordinals of this lambda minus beta minus 1. But this sum is not legitimate. The support is a proper class. Not legitimate. So the fact that this has no inf in the Surreal numbers essentially means that this non-legitimate sum represents a gap in the Surreals, which is similar or akin or related to the gaps considered by the big book, you know, the book, right? This lambda free, omega free, I mean, maybe Vincenzo will say something more. I mean, everything I cannot do, I will do to Vincenzo to explain. So the fact that this has no inf means so psi has no inf. Right? So recall that we have psi. This psi has this lambda initial. To compute the inf, we have to just look at the exponents of this exp. These exponents have no inf in the Surreal numbers, so psi itself has no inf. Thus, no asymptotic integrals. Okay, and now we want to go from asymptotic integrals to actual integrals. Let's see if I can do it in 10 minutes, maybe yes. Okay. So the final part is no as integrals. Okay, you recall that no is the union for M as subgroup of the monomials, but M a set of fields of the form of this form. This is what we call the R omega ON by definition, right? Okay, given one of these, we may close it under derivatives and asymptotic integrals and get another of those, get another R M star, whatever, one of those. Because notice that a field of this form, in order to be closed under the derivatives, it suffices that it's closed under the derivatives of monomials, because derivatives commute with infinite sums. So you just need to add the derivatives of the monomials, and then the derivatives of the derivatives. I mean, by closing under derivatives, you still have a set of objects, not a proper class. Similarly, for asymptotic integrals, if you start with a set and you take the closure under asymptotic integrals and derivatives, you still have a set. So NO is a directed union of fields of the form Rm, which are moreover closed under derivatives and asymptotic integrals. Hence, by previous result, hence also under integrals, not only asymptotic. Because if a field of this form is closed under asymptotic integrals, we showed before that it's actually closed under integrals. And so we are done. So a directed union of fields closed under integrals, of course, is closed under integrals. Thus, no is closed under integrals. And so we need all these lambdas. The lambdas are essentially the integrals of expressions involving the previous lambdas, and you need to add them all in order to be closed under integrals. If you take only set many of them, unless you why the transseries are closed under integrals? If the price to pay is that the transseries are indeed closed under integrals, but are not closed under all possible sums of the monomials that you have around. So you have many monomials which exist in the transseries, for instance, log n times of omega, but you don't have the sum of all those monomials. So either you insist that you want closure under all sums, or you insist that you want integrals. In the surreals, you can do both, but the price to be paid is that it's no longer a set, it's a proper class. So there are some trade-offs. Being a set, being closed under sum, being closed under integrals. And in the Surreals, we are in this situation in which we have all, but we have a proper class. So just in time. So it's 10 to 5. And so I just finished perfectly on time.
Thank you, Alessandro.
Okay. Thank you very much.
I stopped the recording.